In this video, we'll study the chemistry of the simplest family of organic compounds, the alkanes. Alkanes provide a useful vehicle for introducing some important general ideas like the basic approach to naming organic compounds and other topics of utter importance in understanding biological organic chemistry. So let's start with defining functional groups. Functional groups are the structural features that make it possible to classify compounds into families. But we're not going much into detail about functional groups because in this video, alkanes is our primary functional group, so when we go into naming alkanes later, each will end with ane as suffix. If we imagine joining 3, 4, 5, or even more carbon atoms by carbon-carbon single bonds, we can generate the large family of molecules called alkanes. So, their structures look mostly like these examples. Alkanes are described as hydrocarbons because they only contain carbon and hydrogen atoms. If we go back in these examples, we can see here that they are only composed of carbon and hydrogen atoms. On the other hand, they are also saturated. This is because they only have carbon-carbon and carbon-hydrogen single bonds. It's obvious that there are no other types of bonds here aside from single bonds. If we put this together, we will know that alkanes have the general formula of CnH2n plus 2, where n is the number of carbon atoms. In the actual sketch of their structures, we'll not use this way. Instead, we'll draw using the method where every point here symbolizes for a carbon atom. In naming alkanes, we'll use the IUPAC system of nomenclature. A crucial part of naming alkanes is knowing what parent name to use. Here's a summarized table for the parent names. Again, since we're working on alkanes, each name will end with ane. So, if you only have one carbon, the parent name would be meth, add ane, then we'll get methane. A 2-carbon alkane has a parent name eth, so that would be ethane. 3 carbons, the root is prop, so if I draw a 3-carbon alkane like this, again, we said that every point here symbolizes for a carbon atom, then that would be the structure for propane. A 4-carbon chain has a parent name but, therefore, we'll have butane. For a 5-carbon alkane, we'll have a pentane because the parent name is pent. We can go on from here, but I think you already got the general concept. I actually have the list here until 99 carbons. You can see here that 6 carbons means it's an hexane, 7 heptane, 8 octane, 9 nonane, 10 decane, 11 undecane, 12 dodecane, 13 tridecane, 14 tetradecane, 15 pentadecane, 20 is icos, and so on. So, yes, 30 is triacontane. Until 99, it's nona-nona-contane. Parent names are applicable not only to alkanes, but also to other functional groups, so it's important to understand how you can get the parent name. So far, we've only talked about straight-chain alkanes or normal alkanes. They're called straight-chain alkanes because, as you can see here, the structures just went in a line. But what about if you get an alkane like this? An alkane structure like this is called a branched chain alkane because there is something coming off from this carbon chain. So you see, it's no longer a carbon atom one after another because there is now something attached to this particular carbon atom. This something coming off here is called a substituent. It's a group or groups that are connected to the parent chain. So, there, a substituent is now added to the parent chain. To name this, first you have to locate the longest carbon chain, a skill you have to develop in naming functional groups using IUPAC nomenclature. Okay, so let's locate the longest carbon chain. This is very obvious. It's this one, and it has 1, 2, 3, 4, 5, 6, 7 carbon atoms. So this 7 carbon parent chain will have a parent name hept, so this will be called heptane. So, how are we going to name this substituent? First, we'll have to number the carbons from 1. So, in this particular structure, I'm going to start here. So, this is 1, this is the second carbon, this is the third, the fourth, the fifth, the sixth, and the seventh. I started here because this will give us a lower number as locant. A locant specifies where exactly the substituent is located or in which carbon atom it is attached. If we started from right, this carbon atom would be 5 and not 3. We need a lower locant for our substituent, so this is what will follow. Now, this substituent is actually called an alkyl group. Since it is not an alkane but an alkyl, the ending will be YL, not A and E. But we're still going to use the prefixes or parent names we listed here. You see, this one has only one carbon. Yes, this is just a one carbon substituent. So, it will have the prefix meth. And since it is an alkyl, it would be methyl. If we assemble all of this, it would be 3-methyl heptane. Yes, so it's 3-methyl heptane. As simple as that. Let's have another example with 2 or more substituents. First step is to locate the longest carbon chain, so it's right here. And it contains 1, 2, 3, 4, 5, 6, 7, 8 carbon atoms. We can already identify the parent chain as octane. So, that's octane. Next is to number the carbon atoms. If we start from here, the locants for our substituents would be 3, 4, 6, and 7. But if we start from left, that would be 2, 3, 5, and 6. So, obviously, that gave lower numbers as locants, so that's what will follow. So, this is carbon 1, 2, 3, 4, 5, 6, 7, and 8. Okay, so let's move forward to the substituents. This one is a metal, just like in the previous example, and this one as well. So that's 2, 3 dimethyl, because we only have 2 methyls. If we got 3 for an instance, that would be trimethyl, tetramethyl if there are 4, and so on. So again, this is 2,3 dimethyl. Now, this substituent, which is the same from this, have 2 carbon atoms, 1 and 2. So if we base it from the list above, here let's go back to the list. 2 carbons will have a prefix eth, but since this is an alkyl group, not an alkane, these 2 are called ethyls. And that would be 5,6 diethyls because we have 2 ethyls. So again, 5,6 diethyls. Now we have to arrange these parts to get the complete name. We have to arrange it alphabetically. So since letter E comes first before M, it would be 5,6 diethyl 2,3 dimethyl octane. So that's the complete name for this structure. We can actually summarize the nomenclature system for alkanes. It's always the locants first, then the substituents arranged alphabetically, the parent name, and the suffix "ane" since we're working with alkanes. I've prepared more examples here so you can try this. The answer for number 1 is 2-methylpentane. Again, it's 2-methylpentane. While number 2 should be 2,2-dimethylbutane. Again, number 2 should be 2,2-dimethylbutane. For number 3, the complete name is 2245-tetramethylhexane. Again, it should be 2245-tetramethylhexane. And lastly, number 4 should be 4-ethyl. Again, it should be 4-ethyl 2235-tetramethyl-octane. Again, number 4 should be 4-ethyl 2235-tetramethyl-octane. Okay, so how about if the given is the name and not the structure? Like this example, 2,4-dimethylpentane. Well, we'll have to work backwards. First, we'll draw the parent chain, a pentane. So we have to sketch a 5-carbon chain. So 1, 2, 3, 4, 5. And then we have to mark the locants 2 and 4. So this is the 2nd carbon and this is the 4th carbon. This is where we'll attach 2-methyl since it is dimethyl. So carbon 2 will attach a methyl in carbon 4 as well. And that's it. That's the structure for 2,4-dimethylpentane. So you see, alkanes are easy to understand since, as we said, they are the simplest family in all functional groups. As you move on to the next part of this video, in which you learn about cycloalkanes, be sure first that you had understand the concepts we discussed here.
In this video, you would be learning about cycloalkanes. Cycloalkanes are alkanes having its carbon bonded to form a ring. They are also called alcyclic compounds, short for aliphatic cyclic compounds. They all consist of CH2 carbons, since all carbons require to bond twice to form the ring, thus each carbon would only need to bond to 2 hydrogen atoms. The general formula of cycloalkanes is CH2N or CnH2n, with N being the number of carbons found inside the ring. To name the cycloalkanes, we are following rules similar to naming open-chain alkanes. We will now learn the steps to naming cycloalkanes. Step 1 would be to find the parent. You will need to separate the constituent and to count all the number of carbons in each constituent. The constituent having the largest number of carbon would be the parent. The rest of the constituents are considered as substituents. Using the example, we first separate, then count, then find the parent carbon. Step 2. Number the substituents and write their corresponding names. You first need to choose a point of attachment as carbon 1 wherein the second and the other constituents would get their lowest number. Then, you'll need to write their appropriate prefixes after their specified number in alphabetical order. Examples would be these prefixes of a hypothetical compound. We would place ethyl first, then methyl, since it is required to put them in an alphabetical order. It is named 2-ethyl since ethyl is placed at the second carbon. 1,4 is then placed because there are only 2 methyl, thus we also add di as a prefix of the methyl constituents. Cyclo is then added since there would be a cyclo constituent. We would now use this as an example. We first separate the constituents. We can now see that cyclohexane would be the parent carbon. To number the constituents, would start this carbon by going to a counterclockwise direction since the numbering would be lowest. 1, 2, 3, 4, 5, and 6. We would now start to name the constituents starting with this ethyl, so that the name would start with 2-ethyl then going to 2-methyl that is placed at the first and fourth carbon, thus named as 1,4-dimethyl. We now combine it all to get 2-ethyl, 1,4-methyl, cyclohexane.